Hello everyone, my name is Cole and this is the third video in the UP1 exam study guide. So last time we talked about one-dimensional kinematics, just like the general version, the calculus version, and that was right here on your equation sheet. These are the derivatives and integrals, so I'm just going to write those down at the top of our paper to remind us of those. We have that v in some dimension is equal to the derivative of position with respect to time. Acceleration in some dimension is the derivative of velocity in that dimension with respect to time. And conversely, that position is equal to the integral of velocity with respect to time, and velocity is the integral of acceleration with respect to time. Cool. So now we're going to talk about a very specific case of these kinematics where our acceleration is constant. So we're going to be talking about this next part of the equation sheet, which I've labeled with a 3, that has, it says for constant acceleration, and then it has 4 kinematics equations. So the reason that we take the time to actually write equations for this very specific case of constant acceleration is because there's actually not a lot of physical things that we observe where acceleration is not constant. So the most prevalent example is Earth, right? Gravity. We are never really changing gravitational field. So the only scenario where the gravitational field due to the Earth is changing is when we're going really, really, really high up. So a rocket being launched into space. That would be an example of non-constant acceleration. But while we're on the surface of the Earth, I mean, think about it. The gravitational force originates from the core of the Earth, the center of the Earth. And the radius of the Earth is about 600,000 kilometers, I think. I might be wrong about that. It's big, right? The radius of the Earth is very big. So even if I jump really, really high, even if I walk up 10 flights of stairs, my actual distance from the center of the Earth compared to the radius of the Earth, it's very negligible. That distance that I've traveled upwards, which is why we can say that acceleration due to gravity, 9.81 meters per second squared, is very much constant on the surface of the Earth. So that's a really big scenario. That's a scenario where our acceleration is always constant. Another scenario where acceleration is constant is a constant force being applied to something. That is constant acceleration. So for example, pushing on something, on ice, pulling on something, those are constant forces that are being applied. So because this is such a common scenario, we do actually isolate these kinematics equations that we can use off the top of our head if we don't want to use calculus, because using calculus with constants is sometimes a bit overkill. So what I'm going to do now is I'm going to derive these equations. And it's actually really, really easy to derive these equations. It's something that anyone can do on their own, that you can try on your own even right now if you wanted to. But the way we're going to derive them is just setting acceleration equal to a constant. So I'm going to say that A is equal to some constant, and I'm just going to call it A. Okay, it's a number. Constant. Okay. Let's derive some things. Let's start with v. I know that v is equal to the integral of a with respect to time. But a is just a constant, right? A is a. So what do you get when you derive a constant with respect to a variable? Well, you get that constant times that variable. So this is at plus c. Okay. Now, what about that c? Well, that c is going to be based on some initial condition. So if I know that my starting velocity is v naught, that's going to be the c, right? Because at t equals 0, v is going to be equal to a times 0 plus v naught, the starting velocity. So what I get is actually my first kinematics equation, number 1. That is v is equal to v naught plus at. the way they've written it on your equation sheet is like this. That's this one. Vf in some dimension, they're calling it x, is equal to vi in that same dimension, plus the acceleration in that dimension times the time. So the dimensions are very important, and I've omitted them here, but it's important to remember that these are one-dimensional kinematics equations. That doesn't mean that you can't use them if you're working in 3 dimensions. It just means that you do have to split it up into all 3 dimensions. So if I'm working in 2 dimensions, like a projectile, for example, being launched in a parabola, I can still use these equations. I just have to split it up into Vx and Vy, Ax and Ay, and the position in the x direction and the position in the y direction. Okay, so this is number 1. The second one is about position. So let's derive this one. This should be pretty easy because we just found something for velocity. So if we want position, all we have to do is the same thing that we did to find velocity. We just have to integrate it again. So we can say that x is equal to the integral of v with respect to time. Well, what's v? V is v naught plus at. So this is the integral of v naught plus at with respect to time. Okay, so now we get our second kinematics equation, which is that x is equal to this integral. Well, v naught is a constant, so that's going to be v naught t. And then a is a constant multiplied by t, the variable, and when you integrate that, you're going to get 1/2 times a times t squared. This should be starting to look familiar. Okay, and we need a constant here again because it is an indefinite integral. So I'm going to put my plus c there, and then once again, I'm just going to instill an initial condition. I'm going to say that I start at some position x initial is equal to x naught, and since every term has a t in it except for this c, at t equals 0, x is going to must be equal to x naught. So x naught is equal to c. Sorry about that, an alarm went off. It was 11 a.m. And I was very worried that I wasn't up already, clearly. Okay, so I'm going to just add a little footnote here. That means that c is equal to v naught, and this means that c is equal to x naught. Okay, so now we get our second kinematics equations, which is that xf is equal to x naught plus v naught xt plus 1/2 axt squared. This is a good kinematics equation for finding the distance traveled, because what's the distance traveled? The distance traveled, dx, is equal to xf minus x naught, right? Final minus initial, change in position. So yeah, this is if you want to find the final velocity when you know the initial velocity and the acceleration. This is if you want to find the final position, if you know the initial position, the initial velocity, and the acceleration. And here it is on your equation sheet, just like I've written it, right there. Okay, so the other 2 kinematics equations are a little more, not difficult, but less intuitive to derive. It's not just actual calculus to derive them, but we can still find them from what we already have. So let's do that. Okay, so to derive the first equation, what we're going to do is we're going to combine the 2 equations that we have already, and that's actually how we're going to find the fourth equation as well. So the third equation is, I like to call it the timeless equation because it's the only one that doesn't have a t variable in it. So it's actually very useful when they don't give you the time of something. They don't, like the time of flight, for example. And the way we're going to derive it is by getting rid of t. So the way I'm going to get rid of t is I'm going to solve for t. So I'm going to use equation 1, and from equation 1, I'm going to solve for t. I'm going to say I'm going to start calling it vi for initial velocity, or pardon me, I'm going to start calling it vf for final velocity, minus v naught is equal to at. And so then it follows that t is equal to Vf minus V naught over A. And now I'm going to take this value of t and I'm going to plug it into my equation 2. So I have that xf is equal to x naught plus V naught x times my t, which is Vf minus V naught over A, plus 1/2 times my acceleration times my time squared, which is going to be Vf minus V naught squared over A squared. So this is the second or the third kinematics equation, but I'm going to clean it up a little bit so that it looks like what you have on your equation sheet. So the first thing I'm going to do is I'm going to cancel out an a, because there's an a squared in the denominator here and an a in the numerator here, so I can get rid of those. The second thing I'm going to do is I'm actually going to distribute out this square here. And the reason that I'm going to do that is going to become clear. It's because terms are going to actually start canceling out. So I'm also going to distribute this V naught x to here, and then I'm going to distribute out this square. And when I do that, I'm going to get that xf is equal to x naught plus, I'm going to distribute this out. I'm going to say, let's keep it as 1 over a. Like that. And 1 over a is going to be multiplied by V naught x times this whole term in the numerator here. That's going to be V naught x times Vf x minus V naught x squared. Forgot to put my x subscripts there, but it is all in the x direction. This is all in one dimension. Cool, and then I still have this 1/2 here, and I'm going to multiply it by, I have 1/2, and let me be careful, I also have 1 over a, right, because I only canceled 1a. So I have 1 over 2a times this term squared, which is going to be just Vfx squared minus 2 V naught x Vfx plus V naught x squared. Cool. Now I can start actually canceling things out. The first thing I'm going to do is actually multiply by a and move this x naught over to the other side. I'm going to get a times xf minus x naught. Let's take a moment here. Xf minus x naught is the distance traveled, because that's a final position minus an initial position. And that's going to be equal to, well, okay, we have V naught x Vfx, and then we have a 1/2 times 2 times negative 2 V naught x Vfx. So those two terms actually cancel each other out. You can take a moment to look at it. It's this term, I'm going to cross them out, and this term, right? Because it's plus 1 and minus 1/2 times 2 of the same term. So what I'm left with is a times xf minus x naught is equal to negative V naught x squared plus 1/2 Vfx squared plus 1/2 V naught x squared. Okay. One more simplification. This V naught, this negative V naught x squared and this positive 1/2 V naught x squared can be combined, and this is going to become a times xf minus x naught is equal to, this is going to be 1/2 times Vfx squared minus V naught x squared. And finally, we can put this into the format of our third timeless kinematics equation. What I'm going to do is I'm going to multiply this 2 out so that I don't have this term of 1/2, and then I'm just going to move everything but the Vfx squared over to the other side. And what I'm left with is the third kinematics equation, which is Vfx squared is equal to V naught x squared plus 2 times a times, this is the distance traveled, xf minus x naught. And that's the third kinematics equation, exactly as it is on your formula sheet. Right here. And again, that's the one that you're gonna use if you have no time. So it's really important, and I'm gonna post like some examples as well so that you can kind of get a feel for this. It's really important to figure out like when to use which kinematics equation, so that you're not always doing trial and error. If you don't have time, always think about the timeless one. If you have like a distance traveled, for example. If you don't have a distance traveled, but you are looking for a distance traveled and you have acceleration and time, you might want to use the second one. If you're just looking for velocities, that's when the first one comes into play. So yeah, you get a feel for these things. So finally, we can derive the fourth kinematics equation, and the fourth kinematics equation comes directly from the other two equations, the other three equations, I should say. And it's not one that I use very frequently, but it is a very helpful equation in some specific scenarios. And what we're gonna do is, instead of using this equation to solve for time, we're actually gonna use it to solve for acceleration, because this final equation has no acceleration. This is an equation without the term a in it. So it'll be helpful if you don't have acceleration. That's why you don't use it very frequently, because you usually have acceleration, because we're usually on Earth. Either way, I'm gonna take equation 1 and I'm gonna solve for a. Moving everything over to one side and dividing this time by t, I get that a is equal to vf minus v naught over t. Cool. And now I can just plug this into whichever one of these equations I want to. I'm going to do number 2 because it's a whole lot easier. And I'm going to say that xf is equal to x naught plus v naught x times t plus 1/2, and now I'm going to plug in my a, which is vf minus v naught over t times t squared. And once again, this is the equation, but I am going to simplify it. We've got a t in the denominator here and a t squared in the numerator, so one of those t's is going to cancel out like that. And then we can just rearrange our terms. I'm going to distribute out this 1/2. I'm going to turn this into xf is equal to x naught plus v naught xt plus 1/2 vfx minus 1/2 v naught xt. These are both multiplied by t, because I still have a t around here. And now we can combine like terms. This is a v naught xt and a negative 1/2 v naught xt. So what we get is the final fourth kinematics equation, which is that xf is equal to x naught plus, this is all over 2. I've got a positive vfx t, so vfx, and then I'm gonna have one of these should be negative. No, neither of these should be negative. I'm tripping. Sorry about that. This is correct. I had a moment there. We're gonna have a positive vfx and then another positive v naught x, because we have a positive v naught x and then a negative 1/2, and we're keeping it all over 2. So this is gonna be vfx plus v naught x, and it's all multiplied by t. And this is how it's written on your equation sheet. So this is the equation that you're gonna use when you don't have acceleration. Not a very frequent scenario, but here it is right here on your equation sheet. The other thing that I have clearly told myself to mention in this video is this equation here on your equation sheet. It says for constant velocity, delta x is equal to v x times t. So this is a very specific scenario where you have a constant velocity. So a constant velocity means no acceleration, right? Because acceleration is the derivative of velocity, and if velocity is a constant and you derive it, you're going to get 0. So in the case where you have no acceleration, or acceleration is equal to 0, or you're moving at a constant velocity, your change in position is going to just be equal to velocity times time. And this is just actually super intuitive. This is just this equation. Because this is this equation, but a is equal to 0, so you can just completely cross out this term right here. Cool. So I hope that clears up some things about constant acceleration kinematics for you. Remember, very, very important, you cannot use these equations if the acceleration is not constant. So if they give you a function with respect to x or with respect to t or with respect to y for the acceleration, you immediately cannot use these equations. They do not work anymore. You have to integrate. But there are going to be many, many scenarios where you can use these equations. So get used to using them, figuring out when to use them. Use the timeless equation when there's no time. Use the one without acceleration when there's no acceleration. Use this one when you need distance. And, you know, practice makes progress. So, yeah, next time we're going to talk about centripetal acceleration.